I don't have a dog, but I have a cat who would love to walk over my computer and send very cryptic messages.
And how do you keep that from happening?
I close the door.
That's funny. All right, I'm going to show you your joke for the day since it's time here. Appropriate for graduation time. Do you guys know what today is? This is your last day of notes in this class. I know, shocker, right? This is your last new material. How sad is that? Not at all, right? It is really weird though that all of a sudden it's going to end. All right, anybody have any questions from the problem set or anything we've covered so far?
For the problem set,
Yes.
is question 1 a proof? Because it's the let V1, V2, V3 be a basis of, I think, S.
That is a proof.
All right.
Yep. Any other questions? Okay, let's get to notes and make this our last one. All right, we're going to jump. We're not doing section 411 from the book. We're going to jump to section 5.1. It's really important that we cover this. And this section deals with eigenvalues and eigenvectors. I'm going to have to move this over because that's really, really far away. There we go. The first thing I want to do is give you an example of what we're looking for. Just so you can see what we're doing. So we're going to let A be this 2 by 2 matrix. And we're going to have two vectors. U is -1, 1, and V is 2, 1. We want to calculate two different things. We want to find AU. So if you take matrix A times the vector U, what you get is -5, -1. You can verify that if you want, but if you take A times V, you get 4, 2. Now let's look at what this is doing geometrically. So for AU, if I take the vector -1, 1, so here's -1, 1. I'm going to have to make this longer. That's the vector that I'm starting with. And when I multiply that by matrix A, it maps that to the vector -5, -1. So I'm going to go to -5, -1. So it takes this vector here and maps it to that one. Now let's see what the second one did. We started with 2, 1. So there's the vector we started with. And when you multiply it by A, you go to 4, 2. And what we want to focus on in this lesson is this scenario. What we did was took A times that vector and it gave us a multiple of the vector that we started with. Notice that this vector is just a multiple of the one that we started with. It's on exactly the same line. It's just a multiple of that. So we want to focus on that's a very specific situation where you take a matrix times a vector and it ends up just being a scalar multiple of that same vector. Make that bigger. All right, I'm going to write that definition out. It's kind of long. This Greek letter we're dealing with is called lambda. Okay, so here we have both the definition for the eigenvalue and the eigenvector. The eigenvalue is the number, the scalar that gets multiplied by x, and the corresponding vector that works with that is called the eigenvector. See if you're done writing. Okay, let me give you another quick example, just so you see another situation. So x equals 1, negative 1, 1. Oops, this is positive 1. This is the positive 1. It's negative 1, 1. Okay, so if we were to take this, eventually we're going to develop a way to find the eigenvalues, but you're told that this matrix has an eigenvalue of lambda equals -2, and that corresponds to an eigenvector of -1, 1. That means if I take -2 times x, which we know is 2, -2, I should get the same thing if I take a times x. So I'm going to take a times x, which in this case would be 1, 3, 4, 2, times -1, 1, and you can verify that it is 2, -2. So the first thing we'll do is we'll find eigenvalues, and then we'll find the vectors that correspond to those. The vectors aren't just kind of floating around. They go with specific values for specific scalar values. Okay, just a note, because I always thought this was a really weird name. So I looked up what eigen was, and it means peculiar to, or characteristic. It's a German word. So this value, lambda equals -2, is not only is it peculiar to that matrix, but it's peculiar to this vector as well, or characteristic of that. Okay, let's develop a way to find eigenvalues first, and then we'll work on the eigenvectors. So we're going to start with what we want to be true. We want ax to be lambda x. And because eventually we're going to factor an x out, I'm going to say this is ax equals lambda times I times x, just to introduce that matrix in there. I'm going to subtract ax from both sides. So 0 would be lambda I x minus ax. So 0 is lambda I minus a times x. And I'm going to switch the order. I'm going to switch it around. So lambda I minus a times x equals 0. Now, if the determinant of that matrix is 0, sorry, not equal to 0, let me write it out. Then what do we know about that system? From the mega theorem. Crickets. Okay, it has only the trivial solution. Right? If the determinant of this matrix is not 0, then the homogeneous system has only the trivial solution. We want the opposite of that. So we want non-trivial solutions. So we're going to find where the determinant of lambda I minus A is equal to 0, and that will give us non-trivial solutions. Okay, we're going to write that out in a theorem. Okay, and that equation is called the characteristic equation of A. Okay, before we do an example, make sure you guys are done writing. You're still writing. Okay, before we do an example, let's take a look at what lambda I minus A is going to be. Oops, I forgot my I. You're always taking the identity matrix that's been multiplied by lambda. So you have lambda on your diagonal entries and 0 everywhere else, and then you're subtracting matrix A. So it's always going to look like this. And I'm going to do a general one first. So you'll have lambda minus A11, and you'll have negative A12, negative A13, etc. This will be negative A21, lambda minus A22, negative A23, etc. All these are just going to be negative. And then down here, you'll have lambda minus A and N. Now, if you expand that out, if you find the determinant of that, you get a polynomial in lambda. Lambda is your variable. This is called the characteristic polynomial.
Is that negative c with the subscript n?
That's just supposed to be a dot. We'll say plus c sub n. Does that help? Okay, now take a look at that polynomial. There are a couple things about this that will tell us things about lambda. How many possible solutions are there for that polynomial? Do you remember from algebra? If I have an nth degree polynomial, how many possible solutions are there? It's been a while, hasn't it?
N?
N possible solutions. Good. So I'm going to write that over here. N possible eigenvalues. So if you have a 3 by 3 matrix, the maximum number of eigenvalues you can have is 3. It doesn't mean there will be 3, but that's the most that you can have. Do you remember how to find all possible rational zeros for a polynomial? Probably not. This is way back in college algebra. The coefficient of the lead term is 1. So every solution to this has to divide the constant term. So every single eigenvalue is going to have to divide whatever that constant term is in the polynomial. All right, let's do an example. Anybody not finished? I didn't look. I think we're good. Okay. We already know what one of them is because I showed you before, but we'll actually find these. So we're going to start by finding lambda I minus A. And I'm not going to write, well, I'll write the whole thing out just so you see it. You won't have to write this out. You can just go straight to your matrix. So it's going to be lambda minus 1 and lambda minus 2 in your diagonal. And then the other ones you just take the opposite of. Then we take the determinant of that matrix and set it equal to 0 and solve it. So the determinant of our matrix, lambda I minus A, is going to be lambda minus 1 times lambda minus 2, since this is a 2 by 2 matrix, minus negative 4 times negative 3. That's going to be lambda squared minus 3 lambda plus 2 minus 12. And if you simplify that, lambda squared minus 3 lambda minus 10. So now we want to find out where that's equal to 0. So I'm going to take that polynomial, lambda squared minus 3 lambda minus 10, set it equal to 0. Going back to what we did at the bottom of the page before, notice that this is our characteristic polynomial, lambda squared minus 3 lambda minus 10. The most number of eigenvalues we can have is 2, and any of them have to divide 10. So we know it's got to be either positive or negative 1, 2, 5, or 10. I'm going to factor this. It's lambda minus 5 times lambda plus 2. So lambda is negative 2 or positive 5. Let's write out a couple theorems here. This tells you how to find the eigenvalues of a triangular matrix. How do you find the determinant of a triangular matrix before I write this out? Do you remember?
The product of the main diagonal.
Yes, the product of the values on the main diagonal. So what's going to happen is your eigenvalues are going to be right on the main diagonal. Okay, if I were to take this matrix and find lambda I minus A, I'm going to get lambda minus 1, 0, 0, 0, 3, negative 1, negative 2. This will be lambda plus 1. This will be lambda minus 2, and then the corner is lambda minus 5. I'm running out of space. And the determinant of that is just going to be the product of those 4 diagonal entries. So your eigenvalues are actually sitting right here. So if you got a triangular matrix, it's nice and easy. That doesn't happen very often, unfortunately. One more theorem, and then we will do eigenvectors. So here's theorem 3. This is going to sound very familiar. Okay, lambda is an eigenvalue of A. It's a solution to the characteristic equation. Lambda I minus A x equals 0 has non-trivial solutions, which is just the reverse of what we're usually doing. So that one just kind of sums up everything we've done. If one of them is true, all three of the others are true. If one of them is false, all the other ones are false. Obviously, if there is no non-trivial solution, then everything else goes out the window. All right, now we need to find eigenvectors. What we want are non-zero vectors so that that is true. Okay, solutions to this. It's called the eigenspace of A. There are three things that it's equivalent to. I'll just say also here. It could also be called the null space of lambda I minus A, because the null space is solutions to a homogeneous system. This is our matrix. It's the kernel of T, where your standard matrix is lambda I minus A. It goes from Rn to Rn. And you can also describe it by saying it's vectors having Ax equals lambda x. So all of those are the same thing. The eigenspace of A can be referred to as any of these three. Okay, let's find some eigenvectors. Okay, here was our example. We were using A equals 1, 3, 4, 2. We found eigenvalues to be -2 and 5. And this isn't going to be any different than what we've done before. When we found a solution, a basis for the solution space of a homogeneous system, that's exactly what we're doing. So what we're going to do is find a basis for the eigenspace of matrix A. And then the eigenvectors will be those basis vectors. Okay, lambda I minus A is going to be lambda minus 1, -3, -4, and lambda minus 2. So we're going to use that for both of them. If lambda is -2, lambda I minus A becomes -3, -3, -4, -4. Substitute -2 in for lambda. Okay, that makes our system of equations lambda I minus A x equals 0 have a matrix that looks like this. Oops, that's 3, -3. And if we put that in reduced row echelon form, what you get is 1, 1, 0, 0, 0, 0. Now remember, we're trying to find non-trivial solutions, so you should have at least one row of zeros every time. If you don't, you've done something wrong. Okay, lead variable is x1. So I'm going to let x2 equal t, and x1 will be -t. Then x1, x2 is t times -1, 1. We have our system written as a linear combination of basis vectors, and that means that our eigenvector is -1, 1. I don't have enough space. Corresponding to lambda equal -2. Let me see if I can get it in here. There we go, barely. So the eigenvector of A corresponding to lambda equals -2 is -1, 1. I'll write that at the top of the next page. It's a really dinky one. All right, let's do the second one. So if lambda equals 5 is our second one, Anybody not see where that's coming from? Good on that? Okay. If I were to write this system out, it would look like this. That's what the system looks like. But let's solve it and figure out what the basis is. So if you solve that system on your calculator, put it in reduced row echelon form, I got 1, -3/4, 0, and then a row of zeros. And again, if you don't have a row of zeros, you got to have a row of zeros, otherwise there won't be any non-trivial solutions. Okay, once again, x2 will be my parameter. So x1 is 3/4 t. I'll write this out. You're not going to have to write this out every time, but I want you to see what it looks like, where it's coming from. So that's t times 3/4 and 1 gives me my basis. So that's my solution. So 3/4, 1. So there's the eigenvector corresponding to lambda equals 5. Okay. There is another example of finding eigenvalues. I can show you what it looks like. I have another example. So I wrote out this example for finding eigenvalues. It's just a little more complicated than the one that we did. And then I have another one, finding eigenvectors. I don't even know where that one is. Anyway, I posted 2 examples on the Blackboard content tab, under the Blackboard content tab. One showing you how to find, another example of how to find eigenvalues, and another example showing how to find eigenvectors, just so that you have a little more practice. So here's the eigenvectors one. So here it shows you, it starts with a 3x3 matrix and shows you how to find the basis for the eigenspace, and then the eigenvectors. And those 2 examples are posted on Blackboard, so you can read through those. I just didn't want to belabor the point and end up going an hour and 15 minutes. So you can look those up. All right, the last thing we have is one theorem. We are not going to prove it, believe it or not. No proofs today. Okay, if we want A to be invertible, then lambda equals 0 can't be an eigenvalue. There is a proof of this in the book if you would like to look at that. Ordinarily, I would prove it, but This one's kind of challenging. So we'll leave it at that. All right, so if I know lambda equals 0 is an eigenvalue, that means A is not invertible. If A is invertible, I know lambda equals 0 is not an eigenvalue. Okay, that's it. That is it for notes. So sad, isn't it? All right, so you should be able to finish up homework. I think the only thing left is 5.1, so that's the homework for this. Your problem set is due on Thursday by 5 after. Can you, sorry, Ashley, I just saw your question. I'll look at it in a second. I'll answer that in a second. Focus on everything else today. So you need to have your problem set in by 5 after 8. Email that to me. We will, I'll collect your problem sets on Thursday. we're just gonna go through a quick list of all the things that you need to study for your test. And then your test will be next Tuesday. We'll cover from 4-4, so that was whatever comes after. I think it was the column space, row space. That was what we started with. It was what came after linear independence, all the way through section 5.1, excluding 4.11. Can you just make a matrix triangular first to make it easier? No. Well, you can, as long as you remember to change the determinant based on what your row operations are. Because if you just multiply if you multiply a row by -3, that changes what the determinant is. Remember that? So I'm guessing it probably would be trickier to do it that way, trying to remember to apply all those than just to, the easiest way is just to find lambda I minus a and throw it in your calculator. Any other questions? 5 of you I can't see. Good morning, Ethan. Okay, so all we have left Thursday, hand and problem set, review a little bit, next Tuesday test. The following Thursday, I will hand out your the take-home portion of your final, which will be due the following Tuesday. And then that Tuesday during class time will be your in-class portion of the final. So there will be a time limit on that in terms of you'll only have a certain amount of time to do that. Okay, that's all I have. So have fun wrapping everything up. Have a good, is today Thursday? I think it is. No, today's Tuesday. I'm so messed up. So don't have a good weekend yet. So I'll see you Thursday morning for some review and collecting your problem set. Have a good one.